Let's create an accelerometer design using element-based modeling technique using SYNPLE module. Okay, so here let's start creating them one by one. So on the left side we have the element library. On the right side we can create these geometries. First I will take a 4O node element, 4 node rigid plate, and then I take a normal rigid plate. I position it just above this one, this plate, and then one more plate I can just position it here. The bottom one will just rotate it by 180 degrees. So you can rotate it on the select that element and then rotate here, rotate left or right. So rotate it by 180 degrees. So now let's start connecting the terminals for them. So we'll go to joints first. We take a plate joint and then rotate it. Select an element, connect it. So first we need to set the dimension. So let's set the dimensions here. 20U, 20U, 22, 7. So here we have unit length 20U and unit number X. So 20U should be multiplied with 22. So that's the dimension on the X scale. Unit width 20U and then unit number Y. That is that needs to be multiplied, so that is the dimension on the y-axis. So now on the x-axis 20u into 22 is about 440 micrometers, and on the y scale it is 20u and then 7, so that's about 140 micrometers. So we set the same values for other pins also. So we set the same thing for the other elements as well. 20u, 20u, 22, 7. So we set this, okay, and then we take a plate joint here as well. Just rotate it. So now to see how it is going, we can export this file. So first we need to save the file. So I'll just save this file. So to view this, we need to use this element called as global frame of reference. So let's use this one. We need to connect some pins here. So for that we go to sources, constant. So we connect them. We connect a general AC source for the Y pin. So I just save this file. So I can use this option fit all, so I can see the whole geometry. If we want to see the dimensions and want to see what are we trying to design, so you can always push this to mask layout, synthesize mask layout. You can see it has come back. Here you can use this option to see the layer fill. So it can create the mask. So three rectangles are shown here. So on the x-axis it is 440, on the y-axis it is 420, all put together, 140 and 140 and 140. So we use this option of Serpentine. Go to MEMS elements, spring Serpentine 1. So first we will set this, connect it, and then set the value here. So here this 5U is set. So we take one more Serpentine, then rotate it. Okay, so we set this value for this Serpentine, and then we just save the file, and then we will see the mask layout again. So what have we done? So we have connected a Serpentine in the top side. You can see there is a Serpentine like a structure. Okay, so how many turns that the Serpentine should take, what should be the turn width, everything can be seen. So for that you can refer to elements documentation, and there if you search for MEMS element Serpentine 1, so you can see what are all the factors that are there and how do we set it. So these values are explained here. Okay, so the width, length, everything is explained. So similarly for other elements also, you can get the dimensions and also the pin configuration. Okay, so let's set for another two more. So same set of dimension. So what I do is I just copy this same set dimension, paste it here. So I take this one, copy, and then paste it. So here, when I use this copy and paste, so dimensions are all set as it is. So I require the same dimension, so I am using it. So you can see that on the top and bottom side, we have this serpentine like a structure. So this is just for verification. We are not doing any blueprint design here. So we are just verifying the geometry. So now, so far so good. Now there are pins which are open now, so we cannot leave any pins open. Okay, for that we need to use this option called NOT. So on the right side, all the 3 pins gets a NOT. The design, so I can see it in 2D or in 3D geometry. Yeah, so this is what we are trying to create. Okay, so now let's create the comb structures. Beam 2 gap, and another beam 2 gap here on the left side. So here we set this and we just rotate this one. And set these values. So 35 number of fingers. Separation between them is about 2 micrometers. Overlapping is about 30 micrometers. So bottom electrode offset is 10 micrometers. So similarly we set on this one as well. So 40 U. So now we connect it. Okay, just save this file and then see how's it going with synthesizing it in mask layout. So on either sides you can see there are combs that have come. You can see there are combs. Okay, so there seems to be some overlap, so we need to rectify that. Yeah, we have some overlap here, so we need to carefully see what are the parameters that need to be set. So it's 40U, that's fine. 40U, width of the rotor and the stator. A rotor meaning the one which moves, and stator is the one which gets fixed. So 35 number of fingers, separation between them is 30 meters. So how do we rectify that overlapping stuff? So here let's set 1 joint offset 1 0 for the top element. Okay, so for the bottom also we will set. Let's synthesize and see this. Oh, we still have some issue. So you can see that there is some overlap. So this overlap shouldn't be there. So let's carefully look into it again. Yes, I think there is a rectification done. So I had just rotated it thinking that this was this has to be rotated. Okay, but anyways, you keep the sequence 1 2 on this side and 1 and 2 on the other side. Okay, so you retain as it is. So now if we synthesize it, we can see that the geometry looks good. Okay, I think on the right side there is some issue. Oh, I think even that has to be rotated, I guess. So we just delete this bus pin and then just try to rotate it, connect it. Now let us see. Yeah, now it is going good. Yes. So we have it on the right side. There are no overlaps. Okay. So close this. Next, there are pins which are open. So for that we need to connect the knot. I think there are still some more pins like left over. So I need to connect them for the knot. So this is essential for the software to complete the simulation. So there are nothing significant that a knot is very much essential. But for the sake of completing the geometry, we need to use this option of knot. But this does not have any physical significance when we create the geometry. Okay, fine. So now it's almost done. So we need to give input. So we need to do it this way. So here on the top, we use this anchor terminal anchor 3. Okay, anchor 3 for the top one, and then connect one side of the pin. The V side of the pin, can connect it to the ground. So click on this ground button and then click here so you can connect it. So on the other side we use a normal anchor, that is anchor 1. So here at the bottom also we use normal anchor, that is here. So it is all anchored at the corners, at the hinges. That is what we have done. So finally we will see how does it look like now. So everything's fine now. Yeah, all good. Shows this. Here we need to give some input. Without giving any input, we cannot do any kind of analysis. Yeah, so there are some more things that needs to be connected. So we have this bus splitter, connect it, one on the either side of it. So I click here, rotate it, bus splitter. So for that bus splitter, and then wherever we want to see the signal output, we select this and then we click on this area. So here we want to see the displacement in y direction because my input here is in y direction. Okay, so it is connected to y. So here I will change this amplitude of vibration to 49. So what is 49 is 49 divided by 9.8. Why 9.8? Acceleration due to gravity is 9.8 meter per second square. So that is called 1g. So if I'm entering 49, then it is called 5g. Okay. So that's the amplitude of vibration. So here we click here and then we set these values. We can set the offset also to be 49. Click OK. And there are few pins that we need to take care on the bus pin on the beam splitter. So that is general elements, sources, constant. And we go to heatsink. Then we take a heatsink element. Then we connect P to P and T to T pin. So same thing, same activity on the other side. Heatsink, P to P and T to T. So we use this general elements general elements sources constant. Let's run the analysis. Frequency sweep log. So these are the values that we want to set, and we'll see how does this run through. So we set this value. Signals, what are all the signals that we want is all mentioned here. Okay, so these pins B4, B5, B6, if you take a closer look at it, these are the pin connections. Okay, so by default we have connected a element here. So this element wherever gets connected, so that pin automatically gets checked. Okay, so here we click OK as it is. Let's see how does the simulation goes through. So we are all set. We can run the analysis. Okay. So one final check can verify right from the beginning. So these are the values that are set. So on the right side, we will have this option. You can see this final check. All good. It's all fine. So heat sink set. Okay, so now everything is set. Can just go to AC analysis and then frequency sweep 100 to 110K and 201 points in the logarithmic scale and click OK. Okay, so we have this resonance curve that's coming up here. So this is the resonance peak value for the simulation on the frequency analysis. So now we will see some transient simulations. So for transient, we set these values 40M, 10U, signals as it is. So we don't check anything there. And then we click OK. So we are done. We have these capacitance options as a result that it's come. In case if it is not available, check these boxes before running the simulation. So you can just scroll down and find these options. Capacitance top, bottom for both the beam gap. Okay, so now it's appearing for me. So what is capacitance? So what is this? Capacitance bottom, beam to gap 1 versus time. So we have two elements, one on each side. So the top side capacitance between the combs is what it is showing. So it is for one side of the comb. On the left side there are top capacitance and bottom capacitance. So similarly on the left side we have top capacitance and bottom capacitance. So that's what is showing. And now we can play with this data to see how much of capacitance is appearing. So I click on add chart, so I can plot them. So here as well I can plot it, but my interest is to add the signals. So here on the time scale I am interested to add things. So I want to add both the bottom side capacitance. So you can see bottom beam to gap 1, bottom beam to gap 2. So I want to add it. So I will say bottom cap, and I want to add y plus z. Y plus z. So what is y plus z? Y plus z is y and this is z. So I'm adding both of them. I check and then click add signal. I repeat one more time. So this time I am taking top side, top capacitance. So I will add this as top y plus z. Checkbox add signal. Now again I repeat. Now I have to select three signals. So now I have bottom and top put together. I will say it as total capacitance. I select y plus z. Checkbox add signal. Now I can go to this and then select versus time, total capacitance, top capacitance, bottom capacitance. So on this one, I go to add chart. I think total capacitance, I made it as top capacitance, and then I click OK. So this is the total capacitance for the vibrations that are being seen. Fine. So this is the capacitance, total capacitance that we get. So we can take a closer look at it by zooming this to a particular range. Okay, so there are few distortions that comes up. Okay, so this is how we do it on SYNPLE.